Good morning.
Good morning, Rowan.
How are you?
I'm good, thank you. How are you?
I'm doing all right.
Okay, I expect we'll get a few more as time goes on, but we will go ahead and start. I don't have much left to do for chapter 8, but I did, excuse me, I did want to, I was asked if I could give answers to the problems that were at the end of the PowerPoint, which I have done. I've got them. I've posted most of them on the PowerPoint, although it's not on the PowerPoint that's uploaded, but I will go over those in a second. The one thing that I did want to do is talk about this last slide on gas law, real gases as opposed to ideal gases, and answer a question on which gas law to use. Van der Waals studied gases and behavior of gases, and what he recognized was that there were two assumptions made in the ideal gas law. One assumption is that the volume of the particles is so negligible as to be something you didn't even have to consider. In other words, the volume of the particles themselves compared to the volume occupied by the gas was essentially zero. And we do know that gases are matter, and matter has mass and occupies space. So while that is a reasonably good assumption, because gases do occupy very large volumes compared to the volume of the particles, it isn't exactly true. So real gases do have volume, and you have to adjust for that. And that's what you see in this term here, V minus NB. N is Avogadro's number. That means that the volume, what I can say is this: if I was a gas particle occupying a large volume, I can occupy any position in that volume except positions that are already occupied by other gas particles. That means that the space that I can occupy has been reduced by the number of particles or the volume of the other particles that are in that space. And so the actual volume occupied by the gas is somewhat less than the volume of the container. So that's why you have this subtraction here. You have to subtract a value that is consistent with the number of particles present and the nature of those particles themselves. And that's where the B comes in. The B is a constant. It is given for, it is unique for every given gas. And you have a table here that gives you some examples of what those, the value of B is, the constant B for any given gas. So for nitrogen, it's 0.0391 liters per mole, et cetera. And you multiply that by moles, the number of moles of particles in the sample, and you're actually adjusting the volume for the actual volume of the particles. The second assumption made in the ideal gas law that is not true is that particles will not interact with each other. If particles did not have any attraction or repulsion, or repulsive forces between them, but let's think mostly about attraction. If they had no attraction between them, you could not get any condensed states, because it's the attraction between the particles that causes particles to stick together and form liquids or solids. So particles do have attraction for each other. That means that as the particles are moving through the volume of this container, heading towards the walls of the container, remember that the pressure of the gas is recorded as the force of the particles hitting the sides of the container. So if the particles are traveling through this container and moving towards the walls to bounce off the walls, but are instead attracted by other particles, that's going to slow their progress. That's going to hold them back from moving freely through the volume of the container and hitting the sides of the container. So what that means is the actual pressure recorded for the gas is going to be reduced in some way by the attractions of other particles, or it's going to be affected in some way by the attraction of other particles. So you have another term on that adjusts the pressure by A times N squared over V squared. N squared over V squared is the density of the gas. And A is a constant for any specific gas, and you would have to be given that from a table. So these are two constants that were developed, and the van der Waals equation is really just a restatement of PV equals nRT, but it has adjusted the actual pressure and the actual volume to correct for the assumptions made in the ideal gas law that are actually not true. So I will never really, I hate to say never, but I don't like to ask questions asking you to solve problems based on the ideal gas law, because it's really just an algebraic manipulation. It's really very simple. What I want you to understand is what the constants A and B correct for. I don't care whether you can calculate the actual pressure or actual volume for a real gas. What I care is that you understand why real gases behave non-ideally, what causes them to behave non-ideally, and that is the attractions, the actual attractions that occur between particles, and the fact that particles actually do have volume. So I want you to understand what A and B represent. They represent correction factors for those two assumptions. You might be able to, in your discussion of chemistry as you move on, you might be able to look at some of these and understand why the values vary the way they do. Why, for example, does carbon tetrachloride have a much higher value for A? That would suggest that there are stronger intermolecular attractions in carbon tetrachloride than there are in some of these others. Look at water. Water has a very high value for A. That makes some sense because we know that water is very polar, and polar molecules will have stronger intermolecular forces, which we'll discuss in second semester. smaller particles should have lower values of A. You also should notice that the value of A tends to be a much bigger correction factor than B. You can tell by the size of the numbers, the constants B, that the volume correction is relatively minor. And that tells you that our assumption that the particles are volumeless is not really a bad assumption. So knowing what A and B correct for is important. The other thing that's important is to understand when do you have to worry about the real gas law? Under what conditions will gases behave more ideally or conversely less ideally? And we did talk about that last time. We said that at low temperatures, when particles are moving more slowly, they have more time to interact with each other. Low temperatures gases are less likely to behave in an ideal fashion. When they're at high pressures, that generally means that there's a lot of particles around, so there's less space between them. That also is a point at which they will behave less ideally, because the volume of the particles becomes more important, and also because if particles are closer together, they will have more opportunity to interact with each other. So low temperature and high pressure gases are likely to behave in a less ideal fashion.
What was
Yes.
the reason for low temperature again?
Say that again.
What was the reason for low temperature?
At low temperature, the particles are moving more slowly. And because they're moving more slowly, they have more opportunity to interact with each other.
Okay.
So the correction factor for the interactions between particles becomes more important at that point. So conversely, if they behave less ideally at low temperature and high pressure, you can assume that at high temperature and low pressure, they are more likely to behave in an ideal fashion. Now, I will show the answers that I wrote to the questions, but I want to go back for a minute. I was asked a question about how do you know what gas law to use? And this slide actually gives you a hint as to what you have to do and how you figure out, do I use the combined gas law? Do I need to use the ideal gas law? Can I simplify it and do Boyle's law or Charles's law or something like that? You need to read through the question that you're given. And notice I have listed here P1, B1, N1, T1, P2, V2, N2, T2. When you read through the problem, find the values that you're given. You're given a volume here, a 1.5 liter. So you would write down a V1. You're given a pressure here. So you would write down a P1. Go through each of these and figure out what variables have I been given and what am I asked for. In this sample, you're given, this is a simple one, you're given one volume, two pressures, and you're asked for a new volume. So you're being asked to calculate V2. In this case, N1 and T1 don't figure in. So you don't have to use those. Therefore, this boils down to a Boyle's law, P1 V1 equals P2 V2. If you're given a volume and temperature, then it's going to boil down to Charles's law. You do not need to use the ideal gas law unless all four variables are involved. Okay, if you're given a P, a V, an N, and a T, chances are you're being asked, or if usually with the ideal gas law, you're being given three of those variables and being asked to solve for the fourth. For the combined gas law, you may be given P1, V1, and T1, and then two of the variables in the second instance and being asked to calculate the third. But literally going through and taking every number that you're given and identifying it with a variable will help you figure out what gas law you should use. I am highly unlikely to ask you to do a real gas law problem. So you're basically working off of either the ideal gas law, the combined gas law, or one of the simple gas laws. Does that answer your question, Chow?
Yes, it does. And I just have another question about non-ideal gas law.
Sure.
Are we gonna have to know how to calculate it by using the equation?
No, I would never ask you. I would always, if I asked you to solve for it, I would have to give you the values of A and B, and I would give you the gas law. I would not expect you to memorize the van der Waals equation. It's too complex.
Okay, but we do have to know that for the exam, right?
I want you, as I say, I want you may be asked a question about gases behaving non-ideally, but you're probably not going to be asked to calculate them. I have in the past given questions where I have given students a value for A and a value for B and asked them to calculate the ideal, calculate pressure, for example, or something based on of a sample of a gas based on the ideal gas law, and then recalculate it using the real gas law. But it really is just a very simple algebraic manipulation. And so it doesn't really, the only thing that it does is it often will give you an opportunity to see how close those two values are. If your temperature is high enough and your pressure is low enough, you can see that really the ideal gas law is a pretty good approximation. But that's really just an exercise in you being thinking, oh, look at that. It's really pretty good. The assumptions that you make in the ideal gas law actually work pretty well. But that's it's really a simple exercise and not really worth the time. So I probably will not be giving you a question like that.
Okay, that's great. Thank you.
Okay. So I did do these. If you want to write down the answers and check if you've done these problems, in stoichiometry, the answer to number 1 was 4.91 liters. And the volume in the second case was 20.4 liters. For these problems on density and molar mass, in the first one, the molar mass was 2.016 grams per mole. Anybody know what gas that is?
Hydrogen.
Hydrogen, thank you. The second one, cyclopropane, you calculate the molar mass to be 42 grams per mole. If you calculate the mass of the empirical formula CH2, that comes out to be 14. So the answer is, so there are 3 formulas in one molecular formula. So the molecular formula is C3H6. And in the last one, you calculate the empirical formula the way you've done it all along, using the percentages, assuming 100 grams, et cetera. And you get the empirical formula for acetylene is CH. And when you calculate the molar mass, it's 26.1 grams per mole. So it is C2H2 is the molecular formula for acetylene. So that was the density ones. For this one, law of partial pressures, the first one, you calculate the partial pressure of each of those gases. For hydrogen, it's 0.00632 atmospheres. For helium, it's 0.00253 atmospheres. And for neon, it's 7.5 times 10 to the minus 4 atmospheres. I forgot to put the unit there, I'm sorry. And then when you add them together, it's 0.00961 atmospheres. And the part C, if you actually total up the moles of the 3 gases and then calculate it once, calculated as P total, you get 0.00960. The slight difference here is just rounding errors, rounding differences when you calculate each of them individually versus when you calculate them together, and that's de minimis. And the last question, what is the partial pressure and total pressure of a mixture? With these masses, you're going to have to convert that to moles, moles of hydrogen, moles of nitrogen, moles of argon, and then calculate the partial pressures. And it's 1.19 atmospheres for hydrogen, 0.429 atmospheres for nitrogen, and 0.246 atmospheres for argon. Total is 1.86. It's actually 1.865. If you remember our rounding rules, we round so that the number before is even. And since it's already even, you do not round up. But I would not mark that wrong if you wrote that as 1.87 atmospheres. This next one, I did not put the answers on the slide because I just flat out didn't have a lot of room here. But what is the partial pressure of oxygen? It's 0.963 atmospheres. How many moles of oxygen? So for this, of the partial pressure of oxygen, you're simply taking the total pressure and subtracting out the pressure of water at that temperature, which at 30 degrees is 31.8 torr. So you subtract 31.8 torr from the 764 torr, and then I converted that to atmospheres because I'm going to use the ideal gas law, so I have to convert it to atmospheres. So it was 0.963. The number of moles of oxygen collected, you're using the ideal gas law here. Remember, you have to convert temperature to Kelvin. And you solve the ideal gas law for N, and you end up with 0.217 moles of oxygen. And then what volume would the dry oxygen have under the same conditions of temperature and pressure? So we're going to use not the pressure of the water, but we're going to use this total pressure of 764 and the same temperature as before, and recalculate what the dry oxygen, what volume the dry oxygen would have under those conditions. And it ends up being 0.537 liters, 0.537 liters under those conditions. And this one, I've given a similar question on quizzes before, so pay attention on this one. I like the decomposition of chlorates. When you decompose chlorates, they form the chloride salt and oxygen gas. And this is a very common way of generating oxygen gas. So oxygen gas in this way is produced and collected by water displacement. 22 degrees is roughly common room temperature. And you're given the pressure. This pressure would be the pressure in the room at the time the gas was collected. And so it's the pressure inside the bottle. You know that the pressure inside the bottle has to equal the pressure outside the container because if it weren't, the container would either explode or collapse. So the pressure has to be equal. So it's the same pressure that's in the room. But using the ideal gas law, and remember again that you have to convert, notice that we almost always give you the pressure in torr. That's because you're going to have the vapor pressure of water is going to be in torr. So you're going to have to subtract that first and then convert that to atmospheres. And you are going to have to convert temperature to Kelvin as usual. And when you do that, you end up that it's you end up collecting 0.2. That's a decimal. Excuse me. 0.2. Sorry. 0.0259 moles of oxygen is what's collected. That's a zero. That's how many moles of oxygen have been collected. You then use stoichiometry. If you know moles of oxygen, That allows you to go back to moles of potassium chlorate that were decomposed. And when you get moles of potassium chlorate, you can get the mass. And the mass was 2.11 grams of potassium chlorate were decomposed in this reaction. So this, I like that kind of question because it's asking you to use all of the skills that you've used thus far, or that you've learned thus far. You have to use the ideal gas law. You have to use stoichiometry. If I were really being selective about it, if I were giving you a paper, pen and pencil and paper exam, I would probably not give you the equation. I would make you write the equation and balance it, and then calculate using the ideal gas law and stoichiometry and all of that. So this is actually pulling together all of the skills that you have learned so far this semester. In Graham's law, we calculate the ratio of the rate of a fusion for hydrogen to the rate of a fusion of oxygen, and that is 4.76. That means that hydrogen effuses 4.76 times faster than oxygen in the same chamber. The second one, I'm telling you about the effusion rate for xenon, and asking you, under the same conditions, do you expect the effusion of neon to take longer or shorter? And the answer is shorter. Can somebody tell me why?
Is it
Sure.
neon
Actually, neon is smaller.
or xenon or
Yes, xenon. Okay, remember that if we have rate, this is the rate of a fusion of X, and we're comparing it to the rate of a fusion of Y. They are inversely proportional to the molar masses. So it's 1 over the molar mass. So it's equal to the molar mass, square root of the molar mass of Y over the square root of the molar mass of X. Okay, so in this case, it's inversely proportional to the molar mass. So a lighter particle is always going to effuse faster. They have faster velocities and will move faster and effuse faster. And then you can use this equation, plugging in the rate for each of these. Notice the rate is the particle count per time, which we can do as moles. If you can calculate the rate as 4.46 times 10 to the minus 5th moles of xenon divided by 243 seconds, that's going to give you a mole per second rate for xenon. And you're being asked to calculate the rate for neon. You know their molar masses, so you can plug in the molar mass part of the equation. The only thing that you have to solve for is the rate of effusion for neon. Once you get that rate, the rate is going to equal moles per unit time. You have the moles, you've been given the moles, you've calculated the rate. The only thing you need to calculate is the time, and it ends up being 95 seconds. And a gas of unknown identity diffuses at a rate of 83.3 milliliters per second in a diffusion apparatus in which carbon dioxide diffuses at a rate of 102 milliliters per second. Calculate the molar mass of the unknown gas. One question I'm always asked is, does it matter which goes on top? If you put the 83.3 on top or the 102 on top, the answer is no. You'll get the same answer no matter which way you do it. I like to put the larger number on top only because I don't end up with fractions that way, but it really doesn't matter. You'll get the same answer every time, and it ends up being 66 grams per mole is the molar mass of your unknown gas. So, any questions about gas laws? before we move on?
Yes, Professor.
Yes.
So, in summary, gases are non-ideal at low temperature and pressure because of its molecular attraction and volume of molecules, right?
Yes.
Okay.
Okay, so you will be having a quiz on Thursday. This will not affect your quiz next week. Next week, you can still expect the quiz to be Tuesday. I just wanted to make sure we really wrapped up chapter 8 before I gave you the second quiz on chapter 8. And next week, you will be having, next Tuesday, you'll have a quiz on chapter 9, which will start.
Do we have a date for the final exam yet?
You do, and I apologize, I didn't look it up. I believe you do have it. I just don't remember when it is. I'll
It's December 17th at 12:30.
thank you. December 17th at 12:30. Okay.
Are we gonna get like more of an idea of what we should be focusing on for the final?
Sure. Well, you're gonna definitely, as I said, it'll have 50% of chapter 8 and 9 and about 50% review material. I've just given you an example of what I mean by review material, though. There will be some questions that are definitely on earlier material, that are strictly on earlier material. Then you may have, I would say if you look at your quizzes or tests, you'll see material that's very, very similar. But that example that I just gave you of a question that I like to ask is how I could work in old material into questions on chapter 8 or chapter 9.
Right. Okay.
Okay. Okay, so this is one of the chapters that I really like is thermochemistry. Thermochemistry is really the study of energy, and one of the simplest answers to most chemical questions or most chemistry questions, you might ask, why does one reaction occur and another one not? And the answer is probably tied up somehow in energy. So we're going to talk a little bit about energy and we'll get started on that today. Energy can be defined as the capacity to supply heat or do work. And there are many categories of energy, but in broad categories, there are really two. One is potential energy. That is the energy an object has because of its relative position or composition or condition. So potential energy, energy in bonds is really a potential energy. Water coming over a dam, the water has high potential energy. As it falls, that potential energy is converted into kinetic energy, the movement of the water. But it is the higher it is, the higher the waterfall, the higher the potential energy that water has. So energy is based on its position. You have a little car on a roller coaster here. This car has very high potential energy. As it rolls forward, that potential energy where it is at W is going to be converted into kinetic energy. That's the energy of motion as it comes down. When it reaches the bottom here, it's at its lowest potential energy, but it may be at its highest kinetic energy at that point. So energy can be converted from one form to another. You can convert potential energy into kinetic energy. When it comes down here to the bottom, this car can convert some of that kinetic energy back into rising up this hill. That kinetic energy is being converted back into potential energy as the car slows down, but its position moves higher, so it's gained potential energy, etc. So energy can be converted from one form to another, but all of the energy present before the change occurs always exists in some form after the change is completed. Some of that energy can be converted into heat, which is another form of energy, but the energy, the total amount of energy is conserved. So thermal energy is kinetic energy, and it's associated with the random movements of atoms and molecules. So when something is, if we look at these two samples of hot water and cold water, the kinetic energy of the hot water is going to be much higher. Those particles are going to be moving more rapidly. The cold water, the molecules will be moving more slowly. The temperature, hot or cold, a temperature is actually a quantitative measure of hot or cold. So when you measure the temperature of something, it is related to its thermal energy, but it is not a measure of the energy itself. It's related to the energy. Heat is the transfer of energy, and energy always transfers from a warm body to a cold body. So if you have these two samples of water and they come into contact with each other, the heat will flow from the warm water or the hot water into the cold water, warming the particles on that side. So energy is leaving from the left and moving into the right, and it continues to move until the two sides reach what we consider thermal equilibrium. Both sides have the same temperature. That's why when you sit your hot coffee on the counter, it's going to transfer heat to the air around your cup until your coffee becomes the same temperature as room temperature. That's why your coffee cools down, because the heat transfers that energy. It's not a closed system, so energy can move freely from your coffee cup to the surrounding area. You're probably familiar with the terms endothermic and exothermic.
Wait, Professor.
Yes.
I'm sorry. Could you go back really quick?
Sure.
I'm sorry, I don't know if you mentioned it, but why is there a Q there next to heat?
Oh, because I'm sorry. This is Q is the variable we're going to use for heat.
Oh, okay, great. Thank you.
Sorry.
No,
Yeah, we're going to use Q for heat. Remember, and I will go back one more and say that energy can be defined as the capacity to supply heat or do work. This is going to be lowercase q, and this is going to be W. So Q and W are the variables that we're going to be using. Thank you for asking that. I'm sorry.
Thank you.
Matter undergoing chemical changes and physical changes can release or absorb heat. A change that releases heat is called an exothermic process. The heat is leaving. That's because we always define our terms in terms of the system that we're looking at. And we'll talk a little bit more about the system in a minute. But when you have a chemical reaction that is giving off heat, we call that an exothermic process. When a reaction or a change absorbs heat, that's an endothermic process. It's drawing heat in. So we can think of heat as either a product or a reactant. If something is exothermic, it's giving off heat. Heat is a reactant, so is a product rather. So here we have the combustion of methane. Our reactants are methane and oxygen, and our products are carbon dioxide and heat. Okay, that delta, that red delta indicates that we're giving off heat. Okay, and we'll use that. That delta means a heat change, and that's why delta, uppercase delta, Greek delta, means change in any unit, and that means a change in heat. When you have water going from a liquid to a solid, it is giving off heat. It is getting colder. It's giving off heat to the surroundings. That is also exothermic. So we have that delta as a product. If, however, we take that ice and our frozen water and we want to melt it, we have to supply heat for that to happen. In this case, our delta is a reactant. So the heat is a reactant. It's heat that's going into this system as a reactant to generate enough heat to melt our water. So we can think of heat as a product or a reactant in our exothermic and endothermic processes. So let's look at some of these, and anybody can jump in and tell me what you think. Classify these as either endo or exothermic processes. Think about which way is the heat flowing. I'll do the first one for you. If you are touching ice, if you're holding an ice cube, your hand feels cold. Remember that heat is flowing from the warm body to the cold body. So which way is the heat going? The heat, even though your hand feels cold, your hand is transferring heat to the ice, okay, to melt the ice. So when your hand feels cold, that's exothermic. You're giving off heat to melt the ice. The ice gets warmer upon touching it. Is that endothermic or exothermic?
Endo for the ice.
Endo for the ice. This is endothermic for the ice. The ice is absorbing that heat. Water boils in a kettle being heated on the stove. Is that an endothermic process or an exothermic process?
Is that endo?
It is endo. You have to put heat in order to get the water to boil. So that is an endothermic process. Water vapor condenses on a cold pipe. Also happens in the wintertime on your windows. Sometimes water vapor will condense. Is that an endothermic process or an exothermic process?
Endo.
Okay, this is water. Let's write it out. We have water H2O going from a liquid to H2O going H2O as a solid. It's actually giving off heat. It's losing heat as it condenses. So this is an exothermic process. Ice cream melts.
Wouldn't it be from a gas to
That's endo.
It's absorbing heat. So it's endothermic. Water freezes.
Professor?
Yes.
Exo.
For D, wouldn't it be for water H2O gas to a liquid, not liquid?
Oh, I'm
to a
sorry.
solid?
You're right. I'm sorry. You're absolutely right. This is a gas and this is a liquid. You're absolutely right. My bad. Okay. Hydrogen gas and oxygen gas react violently to form water. Would that be exothermic or endothermic?
Exo.
That's exothermic. It's reacting violently to form water. So this is an exothermic process. It is giving off heat. So which is lower in energy? We have H2 gas plus O2 gas on the reactant side and H2O on the water side. This is a 2, this is a 2. Okay, which is lower in energy? The left side, the reactants, or the right side?
Wouldn't it be the right side?
I'm going to put that plus heat over here. It's an exothermic process. The one that's lower in energy is actually the water. How do we know that? Because it's giving off energy. Okay, so the energy contained on this side of the equation is now represented by two things. It's represented by the energy in the water plus the heat that it's given off. Does that make sense? So hydrogen and oxygen are higher energy than water. Water is lower energy. The product here in an exothermic process is lower energy than the reactants. That excess,
Question. So for like an endothermic reaction, the reactants would have lower energy?
yes, exactly. Products would be higher energy. If you're adding energy in, then the product is at higher energy than the reactants. Exactly. Exactly. Okay. So let's talk about the units of energy. You're probably familiar with the calorie. A calorie is defined as the amount of energy required to increase the temperature of 1 gram of water by 1 degree Celsius. That is what a calorie is. It is not the SI system unit for energy, but it is one that you're familiar with. Please note, though, that the calories that you count in food are calories with a capital C. It's really a kilocalorie. So when they tell you that something something has 60 calories in it, it actually has 60 kilocalories. The food calories are actually kilocalories or calories with a capital C. Normal calories have a lowercase c, and a lowercase c is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. It is equal to 4.184 joules. Okay, that's the modern unit.
Wait.
Yes.
When we're looking at calories, we're supposed to assume kilocalories?
No, I'm just telling you that for when you're counting calories for food, just know that it's kilocalories. When you're doing your problems here, it will be in calories, lowercase c.
Okay.
Okay. So how does these all relate to each other? Let's take a look. A joule is a Newton meter. Another way of writing that is a kilogram times meter squared, because a Newton is kilogram dot meter divided by second squared. And Newton meter would be kilogram meter squared per second squared. So how does that relate to energy? If we look over here, you can see that work, if you're pushing something, if you're pushing a box across the floor, it's the force that you're putting on the box, which is the newtons, times the distance that box moves. So force is in newtons and distance is in meters. So a Newton meter. That's a measure of the work that you're doing to push that box across the floor. If you're talking about pressure and volume work, the work is divided by the pressure, which is force per unit area, and the change in volume. This is the kind of work that's done in a piston in your automobile when a gas expands and pushes back against the piston in your automobile. So in this case, pressure is force per unit area. Force is the Newton divided by meters squared times volume. Volume will be in meters squared. And when we reduce that, we end up with a Newton meter, which is a joule. So the work that is done in the gas expanding in a piston is in joules or Newton meters, the same as it is for pushing that box. For kinetic energy, we have 1/2 mv squared. Mass is in kilograms. Velocity is meters per second, and that's squared. So kilogram meters squared per second squared, there we have it, 1 joule. So kinetic energy is also in joules. And potential energy is mass times the force of gravity times the height that it falls, mass in kilograms, gravity is meters per second, and the height that something falls due to the force of gravity is meters, and you again end up with kilograms times meters squared per second squared. So everything goes back to the joule. Just remember, when you're trying to cancel units, when you're given complex problems and you have to cancel units, you need to remember that 1 joule is a Newton meter, or it is 1 kilogram times meters squared per second squared. That will allow you to cancel your units appropriately. Sometimes if you just write it as 1,000 joules, then you don't know how to cancel your units. So that's why we go through this exercise. Okay, so heat capacity is actually a measure of how something responds to heat being applied. So how quickly or slowly does something absorb or give off heat? The heat capacity of a body of matter is the quantity of heat, again, there we have Q, that's heat, that it absorbs or releases when it experiences a temperature change. Remember I told you that capital delta, the Greek letter delta means change. So delta T means change in temperature. So the quantity of heat that it absorbs or releases when it experiences a temperature change of 1 degree Celsius, or equivalently 1 Kelvin. I will point out to you that in gas law problems, you must have temperature in Kelvin. It's critical that you have temperature in Kelvin. The problems will not work if you don't. When we're talking about energy, though, we're generally talking about change in temperature. And change in temperature is final temperature minus initial temperature. That's the change in temperature. Yes.
She found a cheese at the shop.
I'm so sorry, my sister. I'm so sorry. I didn't even realize I was unmuted.
Okay. So change in temperature, because you're doing the change in temperature and you're taking the final, subtracting the initial, it doesn't have to be in Kelvin. It can still be in Celsius, because the magnitude of the degree is exactly the same. The difference between Kelvin and Celsius is simply an offset of the scale. It's where the 0 is. It's offset by 273. But the size of the degree is the same. So it doesn't have to, you don't have to convert Celsius to Kelvin. If you're given heat capacity in units of degrees, of units of Kelvin, you can still use Celsius. You don't have to do the conversion. So heat capacity actually depends both on the type of matter that you're talking about and the amount of matter. So we have 2 frying pans here. These are both the same material. They're both iron frying pans. You have a small pan and you have a large pan. The heat capacity, how they respond to being heated, depends upon the nature of the material. So it takes more heat to heat the larger pan. It takes a lot more heat to heat the larger pan than it does to heat the smaller pan. It needs to absorb more heat to raise its temperature because there's more material there. However, specific heat is related to what material it is. If you calculate the specific heat for each of these pans, you end up with the exact same number. Specific heat is in joules per gram degrees Celsius. So let's go back for a minute. Notice that it takes 90,700 joules to raise the temperature of this large pan by 50 degrees. That's joules per degree Celsius. But if you consider the mass of each of those pans, here, this pan is 4,040 grams. The smaller pan is 808 grams. If you consider the mass of the pans, the specific heat is the same, because the specific heat is defined as the amount of heat required to raise 1 gram of a substance by 1 degree Celsius or 1 degree Kelvin. Whereas this example is how much does it take to raise the temperature of this entire pan compared to this smaller pan. Here, we're talking about 1 gram, and it doesn't matter whether you're talking about 1 gram from the small pan or 1 gram from the large pan. 1 gram of iron requires 0.449 joules to raise its temperature by 1 degree Celsius. So the specific heat does not depend upon the amount of matter present. It will be, and therefore it is an intensive property. See, now we're going back to material we did at the beginning of the year. It is an intensive property. It is a property that can help you identify the what a substance is, if you can calculate its specific heat. So here is a table of specific heats for a variety of substances. If you know the mass of an object and its specific heat, you can determine the heat change due to a temperature change. And the equation that you use is Q, which is heat. Heat equals mass times specific heat, which is C times the change in temperature times delta T. And change in temperature is always the final temperature minus the initial temperature. That would be the change in temperature. If something is cooling off, its change in temperature is going to be negative, and Q will be negative. If something is heating up, then delta T will be positive and Q will be positive. Okay, so here are some specific heats of a variety of substances. You'll notice here that copper, lead, iron, all of the metals tend to be very low specific heats. Water has a very high specific heat. And that's actually really important, particularly to the organisms that live in water. How many of you have gone to the beach in the summertime, early in the summer, maybe May or early June, and you stick your foot in the ocean and the ocean is really cold? The air temperature is nice and warm, but the water temperature is pretty cold. That's because air heats up faster than water. So the water temperature has it, because it has a very high specific heat, heats up very slowly. If you go to the beach in the fall, after a whole summer of hot temperatures, and the air temperature might be colder because you're in late October, early November, but the water temperature is going to be warm. That's because water has a very high specific heat, so it gives off heat very slowly. Okay, so it heats up slowly, it cools down slowly. And I said that was very important for the organisms that live in water. And the reason for that is that the range of water temperatures varies much lower degree than air temperature. And most organisms that live in water have a very narrow range of temperatures that they can survive at. That's why you see animals migrating with winter and summer. They are migrating because they have a very narrow temperature at which they are comfortable, and they need to stay where the water is within that range of temperatures. So they'll migrate accordingly, and they'll go to warmer water if they need it, or they'll go to colder water if they need it. This is why our warming planet is really bad for the organisms that live in water, because water has, our ocean temperatures are rising, our river and lake temperatures are rising, and it is changing the environment for the organisms that live there. And you'll find that some populations of organisms that live in those bodies of water may be disappearing because the water temperatures are not staying within a range that they can survive. That all is because water has a very high specific heat. We make our cooking utensils out of metals. Why? Because they have very low specific heats. They heat up quickly, they give off that heat quickly, so they can transfer that heat from your the gas flame on your stove, they can transfer that heat to the food that's being cooked, and they transfer it very readily to the food that's being cooked. So we want something with a very low specific heat to make our cooking utensils out of. That allows us to use less energy to raise the temperature of that pan and transfer that heat to the food. So it takes us less energy to cook than it would if we were cooking with something that had a much higher water specific heat. Does that make sense to everyone? Okay, so we have a couple of problems here, and I can do, I'll do these for you, at least the first couple. Let me change my, okay. Okay, so the first question I had there was this one. How much heat in joules must be added to a 3.5 kilogram iron skillet to increase its temperature from 25 degrees to 250 degrees? This is the equation that I'm going to use. Q equals mass times specific heat times delta T. And the C for iron, the specific heat for iron is 0.449 joules per gram degree Celsius. Now my mass, because this is in grams, my mass also has to be in grams. And I also have to figure out what delta T is. Delta T is equal to T final minus T initial, which is equal to 250 degrees Celsius minus 25 degrees Celsius, which equals 225 degrees Celsius. So Q equals 3,500 grams times 0.449 joules per gram degree Celsius times 225 degrees Celsius. Notice that degrees Celsius cancels, grams cancels, and I end up in joules. And the answer is, rounded to 3 sig figs, is 354,000 joules, which I can write as 354 kilojoules. Okay. I am limited to 3 sig figs. Actually, I probably am limited to 2 because of the 3.5, but I would accept 3 there.
Quick question.
Sure.
Will we always be given the specific heat like we were in this?
Yes, yes. Or I could give you a problem. I could give you a problem where I gave you Q, I gave you mass, and I gave you the means to calculate delta T and ask you to solve for specific heat.
Okay, cool.
Okay.
Thank you.
That's also a possibility.
So in that case, we just switching the equation, right?
Yeah, you just resolve the equation. That's all.
Okay.
In fact, I think that's what this second one is. Okay, so we have a piece of unknown metal that weighs 348 grams. When the metal piece absorbs 6.64 kilojoules of heat, its temperature rises from 22.4 degrees Celsius to 43.6 degrees Celsius. Determine the specific heat of this metal. This could allow you to identify what the metal was. If you if you do this carefully enough and you compare it to a table, you could potentially determine. So let's write down our variables. We have mass is equal to 348 grams. We have the Q. We've given the heat here. That's 6. So Q is equal to 6.64 kilojoules, which I'm going to turn into joules. That's 6,640 joules. Okay. And delta T is T final, 43.6 degrees Celsius minus initial 22.4 degrees Celsius. So my temperature change is 21.2 degrees Celsius. So now I'm going to take my equation, which is Q equals mass times C times delta T, and I'm going to solve that for C. C is equal to Q divided by mass times delta T. So it's equal to 6,640 joules divided by 348 grams times 21.2 degrees Celsius. And when I do that math, I end up with 0.900 joules per gram degrees Celsius. My units are the units of specific heat. So this is the specific heat of our unknown metal here. So let's go back. I'm going to go back here. And I will go back to our screen, because let's go back to our table of specific heats and see if we can guess what this metal might be. We said it was 0.9, so we can look at our table, and if I were to guess, what would you guess? Something around 0.9.
Oxygen.
Well, it's a piece of metal, so we can eliminate oxygen.
Aluminum.
Aluminum.
It's probably aluminum, okay? And that's a pretty good measure. If we ended up with 0.9, that's a pretty good measure of specific heat, okay? So I'm gonna leave this last one for you to do. How much would the temperature of 275 grams of water increase if 36.5 kilojoules of heat were added? So this is your mass. This is your Q. We would have to go back here to use 4.14. That's your C. Okay, so you're using Q equals mass times specific heat times delta T. You have mass, you have C, you have Q. You're solving the equation for delta T. So you're asking, how much would the temperature increase? You're asking for delta T. You're not being asked for the final temperature, because you weren't given the initial temperature. You're just being asked what delta T is. So I'm
sorry, I'm sorry.
Yeah.
Where do you have C?
C
You're
is,
looking at the chart, right?
yes, from looking at the chart. C is, this is the specific heat of water, 4.184.
Okay. And
you should be given the specific heat, or you'll either be given the specific heat or you'll be asked to solve for it. One exception might be water, and that's only because you're going to use that number so often that you will not forget it. 4.184 joules per gram degree Celsius is the specific heat of water. It's a constant that you're going to use so often. In fact, most aqueous solutions, as long as they're dilute enough, most aqueous solutions, you'll use that same specific heat. You'll use the specific heat of water, because in most solutions, the solvent is water. And so unless the solution is really concentrated, the specific heat won't change very much from what the specific heat is for water. So 4.184 is the specific heat for water. And that's what you would use to solve that. So I'm going to let you guys do that one. And I just I'll introduce this, and I think we will probably
Can you go back real quick, Professor?
Sure. You had a question?
Oh, could you just go back to the other slide?
This one?
Okay, thank you.
Okay. I'm going to introduce this next concept, and then we will spend a lot more time with it next time. Calorimetry is the science of measuring heat or heat flow. It's a technique of measuring the amount of heat that's transferred to or from a substance. And there's basically two categories of calorimetry. But a calorimeter is the object that we use to do that. And we have a sample over here where you have a system, and I told you we would talk about what the system is. The system is whatever you're looking at. You might be looking at the neutralization reaction between an acid and a base. There is a heat change that happens with that. It's an exothermic process. So if you have a system in which you have a chemical reaction, for example, that chemical reaction will be your system. It is giving off heat, and it's giving off that heat to the surrounding water, or the surrounding, in this case, water. So if we're mixing an acid and a base, and it gives off heat, the surroundings is the water that reaction is occurring in. The reaction is actually the H plus OH minus forming water, but the heat that reaction gives off is being absorbed by the surrounding water of your aqueous environment. So the temperature, we measure the temperature change. So here we have a case where we can look at the initial temperature here, and the temperature goes up, so we can measure the temperature change. We're measuring the temperature change of that surroundings, and that allows us to calculate the amount of heat that was given off by our reaction. So the system is going to be defined as whatever is undergoing the chemical change, whatever we choose the system to be. The system might be combustion of methane. The system might be, as I said, an acid-base neutralization. The system might be a salt dissolving in water. That will have some energy changes. Some of them are endothermic, some of them are exothermic. But the dissolution of a salt in water might be your system. The surroundings is the rest of the universe. So the system is what you're looking at. The surrounding is essentially the rest of the universe. If you have an insulated calorimeter, notice that this has a very thick wall. This is an insulated system. So our surroundings in this case is just whatever is inside that calorimeter. If the system were open and heat could escape, then you'd have to consider the air molecules in the room. You'd have a much bigger surroundings. So we try to use an insulated system that contains that heat so that we can measure it by the temperature change. So the rest of the components in this case of our apparatus would be the surroundings. So let's look at how that works if we have a piece of hot metal and we drop it into a calorimeter with cool water. So our surroundings here are the water. The metal, our hot metal, is the system. Remember that heat flows from a warm body to the cold body. So the heat will flow from that hot metal to the water. So Q, in this case, this is exothermic. The metal is giving off heat. The water, if you're focusing on the water, that's endothermic. The heat that's being given off by the metal is being absorbed by the water. So we can say that because energy is conserved, whatever heat the metal gives off added to the heat that the water absorbs has to equal zero because of conservation of energy. The heat from the metal is going to be positive. It's exothermic. The heat absorbed by the water has the same magnitude, but an opposite sign. Remember I said that you can get that negative sign or positive sign from the temperature change, okay? So Q for the metal is mass times specific heat times delta T. Heat for the water is mass of the water times the heat capacity of the water times delta T. And if you add all that together, you end up with 0.
Sorry, Professor, where's the M and W from again?
The mass is the mass of the metal, and the mass, M, is the mass of the water. So you have to measure the mass of the water in this system. Okay? Now I actually am going to make one change here. I want to erase this. And I want to erase that. Oh, come on. Give me my eraser. Why does that not want to erase? Well, it's not doing it. Okay. I don't know why it's not erasing it. I wanted to change the
So
sign.
is that we try to find the mass of metal and mass of water, or we try to compare like?
You have to measure the mass. You have to measure the mass of the water. You have to measure the mass of the water in this system. You measure the mass of the water because that is your surroundings. The idea is to determine how much energy is flowing in this system. And in order to do that, you have to use this equation for mass times heat capacity times delta T. And so you have to have the mass of each part of your system. So the metal is your system, the water is your surroundings. But you have to know the mass of each of those independently. Okay, so I actually have these signs. I think these signs are wrong, and that's why I want to cross those out for now, because I want to show you where the signs come from. T final minus T initial this is the metal. Is your metal losing heat or gaining heat in this system?
Losing heat.
Losing.
So T final is going to be lower than T initial. So your delta T here is going to be negative. The water is going to be gaining in temperature. The water is warming up. So T final is going to be higher than T initial. So your delta T here is going to be positive. Put an equal sign in there. But the magnitude of the change, the magnitude of Q for the metal equals the magnitude gained by the water. So that's why you can add these two together and get 0. So why do I say delta T final and I don't have delta T metal final and delta T water final? Why don't I do that?
They'd be at the same final temperature.
They're going to be at the exact same final temperature. And when this comes to thermal equilibrium, T final is T final for the entire system, the entire calorimeter. So the water temperature and the metal temperature are the same. T final is the same. This is a nice exercise for you. T final is the same. Can you take this equation and can you solve that equation for T final? If I were to give you the mass of the water and the mass of the metal and the heat capacity of the metal, the initial temperature of the water, the initial temperature of the metal, could you calculate what the final temperature of the system is? The answer is you should be able to, but you need to rearrange that equation to calculate, to isolate T final. I think that's probably where I would like to stop for today. Let me close that. Yeah, there is some practice I would like you to, you can certainly, I will upload this PowerPoint and you can certainly look at those practice problems and see if you can use this equation to solve the first set of practice problems. But that is where I'm going to stop for today. I think we're in pretty good shape for finishing up this chapter. We have 3 sessions. We have today and Thursday, and we have next Tuesday. And then Friday would be for review. So, any questions?
Yeah, Professor.
Yeah.
How long is the finals? Is it like the regular exam time?
Ooh, I don't know. I think it's longer. I think it's 2 hours. I have to check, but I think it's 2 hours.
Okay.
Can you post those information about the final on like Canvas so we can look at it?
Sure. I think the information should have been posted. You should have access to it through Lion's Den, but I will post it.
Great. And then you said you're gonna post like a final review.
I will
for
give you.
us?
I will try to give you some sort of a review. Once I have to start. I have to actually start. I've started collecting questions for the final, but once I do that, I'll be able to give you some better direction.
Okay.
I probably next week, Tuesday or Thursday, I'll be able to give you much more information on that. We're beginning to compile the questions now. So, and as I said before, I'm not the only one that writes questions. The entire department writes questions, and we pull them, and then we develop the final from that.
Okay. I just have like a question after class, just to take you a couple minutes. Is that okay?
That's fine. Sure.
Okay.
Okay. If we're done, we're done. So see you all for lab tomorrow. You're doing gas laws tomorrow.
See you tomorrow, Professor.
Okay.
Have a nice day.
Have a good day, Professor.
Thank you. You too.
Have a nice day, Professor.
Bye.
Bye. Thank you.
Professor, quick question.
Sure.
I'm not sure if I like missed it, but in chapter 8, did we go over like using like the equation work equals negative pressure times the change?
Oh, no. That comes up in this chapter.
Oh, okay. It was
That
part of the homework that was due, so I was wondering if I missed it or something.
No. It's work equals minus P delta V.
Yeah. Mhm.
That actually comes up in this chapter.
Oh, okay.
Okay.
All right. That makes sense. All right. Thank you.
Okay.
It's a question. Great. So I wonder, can you tell me what exactly I have to get on the final so I can maintain what I have right now, because I can't really do that. Well, it's for me, I want to see it so like I can set a goal for myself.
I have to look at it, Chow. Let me look at it and I'll let you know. Because one of the things that hasn't been done at this point is I have not added any extra credit. I don't know if you've been doing, I don't know if you have been doing the review tests, but the review tests are worth extra credit.
Yeah, I did those.
Okay,
tests.
so I have not added any of that in. I will be dropping the lowest lab. I'll be dropping the lowest quiz. So that's going to raise your grade from where you are. I don't drop those because I don't know, maybe you'll tank on the next quiz. You know, maybe what your lowest quiz is now is not your lowest quiz. Maybe you'll tank the next quiz. So I don't do that until the end of the semester. So it's really hard for me to say, and because I'm going to be doing things that will manipulate your grade in the end.
Right.
I'll try to look at it and see.
Yeah, can you just give me like an estimate so I would know?
Okay.
Because like I need, well, sometimes I like to have like pressure on me, so otherwise I would not do anything.
Then you have to have an A. There you go. You have to have an A. No,
That doesn't lead too much.
I'll look at it and see what I can figure out.
Okay, great. Thank you so much.
Okay.
You
you're
have a
welcome.
nice day.
You too.
Yeah.
And Professor, you're okay with like the tutor session right now, like we talked about last week, right?
Sure, sure.
Alrighty.